So we are the last. So let me say a few words. First of all, I hope everybody had a good time, learned something. If you came here and you only saw things that you were familiar with, that was not the intention. If you came here and didn't learn anything at all, that was also not the intention. I hope you learned a few things. You saw some new ideas, met people, were able to have some conversations, to take a look at what other people are doing. And usually, this applies for us, but also for you. Usually we work in an area, we don't really understand completely what's going on in a different area. We just have glimpses here and there. We hope that you got some more glimpses now than before. And now, before we finish here, we thought it would be a good idea to make this is what we call in South America the paredón. Just come here and you shoot. And quite literally you shoot, because you can have shots here, optional. If you ask a question, you can get a shot here of a very good cachaça. And the person you ask the question to can also have a shot. So in that way, maybe you don't concentrate all questions in a single person, but in all of us. Otherwise, the
or
answers,
maybe yes, depending, right?
Well, there you go. So you have somebody there. Otherwise, we'll have a complete incoherence at the final stages of this. So, so any kind of questions here, okay? So these can be physics questions. It can be like, oh, what do you think about this crazy idea? Or, I started working on this, but I'm thinking about something else. Also, career advice, oh, I'm coming up for my PhD, I don't know what to do. How should I make myself more interesting for the market out there? Any kind of questions are welcome, okay? And like I said, there is extra incentive for that. Oh, optional, of course. If you don't want to drink, that's fine also. So who wants to start? Yes. Do you want a shot? Yeah. Okay.
But I want a shot with you. IP. Yeah. Okay, my question is, Bertuzzo, you were talking about dark matter and all different lines. And yes. I wanted to know which is the line that you work with the theory, because you said so many examples, but I didn't know, which one do you work with?
Well, for a long time I worked with the Frisao models. So, well, I mean, my scientific career started with supersymmetry. I've been a student of Riccardo Barbieri, which was one of the last, how to say, very strong fanatics. I need to digest. Thanks. It was one of the the few last fanatics about supersymmetry when I started, which was more than 10 years ago. Oh my God. And lately I moved to gravitational particle production. Okay. I'm not completely understanding yet what is going on. That's why I didn't talk about my work. But yeah, that's the direction I'm going. Actually, somebody asked me yesterday what I think is actually dark matter, and I don't know, I'm a bit pessimistic. I think it just interacts gravitationally and we won't ever discover what it is. But okay, cheers. Cheers. Yes?
It has been my dream to drink cachaça with you. So cheers.
Yes, by
yeah,
the way,
maybe yes.
Orlando, what are you doing
there?
Why
are you there?
What are you doing there? You come here. Come here.
You're one of the organizers. Come down here.
The guy was thinking, he wanted to ask a question. That's probably.
So Orlando works on neutrinos. Yes. So if you want to ask a question about neutrinos, you have Carlos, you have Armand, you have Orlando.
There you go. This also with incentive or without incentive?
So it's about neutrinos. I don't know, anyone could answer. Do you believe that, what do you think? The neutrinos are Dirac or Majorana particles? So.
He just wanted the drink, of course. Obviously, he doesn't even care who is asking. So you have to choose somebody to ask a question. There you go.
Obviously, didn't use a Mariana practicals. You need to prove on that. No, sorry. No, I think the Mariana are more interesting to get more phenomena that you can investigate, different things like neutrino, anti-neutrino transition. That's something you never saw in the nature, in theoretical. And if you have Mariana, you can say this. And when you have neutrino, anti-neutrino transitions, you open a lot of new possibilities to do, things to do, and then because of this, okay.
Hã? Comer ou cachaça?
Without the cachaça. And also, I think is Majorana, and probably I can argue like this. One of the beauties of a standard model is that you write whatever is possible. There is nothing left, basically. And if there is the possibility to be Majorana for a particle, which for neutrino it is, why not? And that is actually the argument behind many terms you write in the standard model. You write all the possibilities. And that's one guiding line for us. Yeah? If it is possible, it should be. Okay.
Yeah.
Okay, now I'm sorry about that. You are obviously abusing the system. Go ahead.
I mean, it's.
No, I think we need to have the vote of the students if the second and third person should receive the shot or not.
I mean, I'm also a pro Majorana person because I think it's more fun. But this statement that everything that can be written should be written, it's an interesting statement, but so far it's not entirely true because, like, when you have strong interactions, you can have CP violating terms, which so far experiments as should be zero. So it's kind of weird.
So basically, that is the reason you have a symmetry. You say that there should be axion. You look for this because that is like a guiding principle for us. So
Yeah, we will test it.
So can I add? Okay, so actually there are two more terms, right, that we do not understand. Even the Higgs mass we do not understand. I mean, it's there, we measure it, we don't know why it's that small. That's what we call the hierarchy problem. And even worse, much worse by many orders of magnitude, the cosmological constant, we have no idea. So in the Lagrange or the standard model, you can add a constant term that is absolutely, you see, a constant, by definition, respects all possible symmetries you can think of. We know it's there, and it's so much smaller than what we expect that it's, I don't know, would you guys agree it's the largest mystery that nowadays we have in theoretical physics?
It's the largest small number.
Largest small number, exactly.
Okay. Yes. You still want IP or Umburana or clear? You have
So that's actually the reason we did this. So
IP,
you guys
IP. Everybody else.
For Bertuzzo, if you had to bet $1,000, would you say that SUSE particles exist or not? And why?
Okay. Well, I don't think I have that money to bet, but okay. So let's suppose I have. No, I don't think supersymmetry is relevant at low energy. I think it may be relevant at high energy when we talk about string theory. I know that many people don't really like string theory, but I think it's a nice theory, and it's basically the only theory of quantum gravity that we have, which I think is a remarkable accomplishment. And supersymmetry may be relevant, but I don't think it's relevant for the hierarchy problem. So I have the impression we are not understanding anything about the hierarchy problem. Now, why we don't understand, I have no idea. I mean, I've been thinking about that for 10 years, but I still do not have any idea. I don't know. I don't think supersymmetry is out there.
Okay.
Cheers.
Posso fazer outra pergunta? Okay, for Argelis can be, and I don't know, Orlando, Armani. Do you think that sterile neutrino there? And maybe it'd be a dark matter or not?
You already made a bet a few years ago. You remember Orlando? You have to
Yes.
pay that. You
I
said,
win.
You said in 2-3 years will be found.
No, but they found. No, it's okay. It's like in Mariana. Sterile neutrinos are very nice. They have very interesting things you can do. The problem is that I know they say sterile neutrinos is a very hard thing, no, because it's very small effect. And they have this confusion. You have many different results, experimental results. One say they have sterile neutrino, the other say don't have sterile neutrino. It's a mess. I know this. But also, you remember something like 15, 20 years ago, we have got 20 different solutions for solid neutrino problem. Completely different solutions, and at the end, one win. I think it's something you can get, no? But the problem you need to have you need to see something. What you can confuse the physics, you see oscillation, a real oscillation, not a dump, any effect, but a real oscillation of sterile neutrino. If you see this, the people don't like because a light sterile neutrino means that you're not supposed to have a light sterile neutrino. This is you cannot fit well in the theories, no? But you know, there's something that say, John Harris write a review report 1 year before the neutrino oscillation. He say, everything in the standard model is okay. You only need to find the Higgs. For neutrinos, you don't have any problem. You have no oscillation. Let's continue life. You see, it can be that, most of the people don't like sterile neutrino because this is a very low scale. It's a problem to have this very low scale, but can be, no. You cannot choose what your nature choose, no?
I will comment. So that's a good question. I think that it depends what mass of certain neutrinos. Like if neutrinos are Dirac particles, you know, the right-handed neutrino is technically sterile neutrino. So I think most people believe that that should exist. And we could figure out if neutrinos are Dirac particles eventually, if it's not the fun Majorana type. In the experimental anomalies are kind of fun too. I think that we are in it oscillates in how excited we are. Like sometimes we think like it's really there, it's about to get confirmed, and it's like, no. And then we're like depressed and sad. So I think like now we're in like not very optimistic for light sterile neutrinos time, but we will see what happens soon.
So I feel like I feel like before.
Okay.
I knew.
Yeah, so I'm there's an interesting connection to sterile neutrinos to what I said. I don't know much about the particle physics aspects, but sterile neutrino is one of the candidates for warm dark matter, so KV masses. And you can ask, and there's actually been cheers. There's been a lot of discussion that dark matter plus dark energy fits very well a lot of observations from large-scale structure in the universe to cosmic microwave background, but that it fails to produce some of the smaller scale features in the universe, the profiles of the inner parts of galaxies, and also the number of satellites of galaxies, and this could be helped by warm dark matter, which erases fluctuations on small scales because of free streaming. And it turns out that it's very important for what I said, because an obvious consequence of this is you just erase the first black holes and stars that I discussed beyond some redshift, because the small perturbations on small scales, which would have started this process, don't exist. And so actually I think it would be a problem if the dark matter was entirely consisting of warm dark matter, such as few keV sterile neutrinos. You wouldn't.
Okay. I had a very, sorry. I was gonna ask Carlos because I know that he was there when they asked me this question, and it's a very typical question, but I guess I feel bad because it can transcribe to either of you, and you can all question. If I gave you $1 million, but let's be more generous, unlimited funding, what kind of detector would you build? In this case, for Carlos, would be the optimal new detector in neutrino physics that you could do dark matter or just focus on a specific neutrino. Like what, if I gave you money, what is the one thing that you want to discover and find out, and how would you build a detector that does exactly that? And that can be applied to. You want to get all of us? Yes. It's only 5 p.m. somewhere.
Good question. No, 100 million, unlimited money.
Unlimited. Let's, yeah.
Yeah, I mean, I think it's a very biased answer, right? I mean, I like neutrino telescopes, I like high energy neutrinos. I have this idea that, new physics potential is in high energy, so I will build like a huge, very tightly packed water neutrino telescope. I think that, and it's kind of neat because, what we have been doing is a little silly because we take our detectors and we sort of space them equally. There is no reason to space them equally. You can have several spacing scalings, and that'll give you sensitivity for low, intermediate, and high energy. I know many of my neutrino colleagues will put their money on a bigger dune detector, and that's fine too. But I think that you have to be careful with just only doing neutrino flavor physics. There is something interesting in looking at very high scales, and so that's why I like this very large neutrino detector. If you give me that, since it's unlimited, I will also build my detector in the Andes, so it would be nice to have one over here in the south. So that'll be pretty cool.
I can say some. So the title of this.
Anybody else? Yes?
It helps.
I unleashed a beast here.
It helps dream, yeah. But the title of this school is multi-messenger. So for multi-messenger, you want to find gravitational wave sources on the sky with some other photons or neutrinos. I think what I would like is a X-ray telescope or UV telescope with an extremely large field of view, because the gravitational wave localization is generally not very good. So you want a wide field telescope that you can have to yourself, and every time there's a gravitational wave event, you can point and cover, I don't know, 10 square degrees, and just stare there and find the counterparts. I think it's $1 billion.
Don't worry, I got you covered.
Yeah. So I go the same direction. I would just cover the Earth on Einstein telescopes. I mean, with like a icosahedron of Einstein telescopes all over Earth to see. Then we could get the precise position of the sources with. Then you don't need yours. No, but seriously, I think we are being very biased here. I once had a conversation with another cosmologist who was saying this. You know what? If humans find an habitable planet with evidence of life there, everything we're talking about here is just. So I think this is something like a big James Webb times 10 on the infrared for detecting molecules and different planets. This would be probably the biggest discovery ever. But it's that's more than 10 billion.
What about new technologies? Can you think of something so we can patent it right away?
Technology.
Yes.
I want a muon collider. I want a muon collider, please. I really, really want it. With precision, with a lot of energy. So now it's up to you guys. Our generation didn't come up with a good idea. So now it's up to you. Do you agree as well? Do you want a muon collider?
Since the money is unlimited, let me also propose another one so we can have more than
Okay.
this. I also go for an 10 times better Fermi-Lat experiments. Gamma rays, especially going to the high energy gamma rays, TeV gamma rays and also MEV gamma rays. And that is a gap in our understanding of the universe. I believe Fermilab changed our view of the universe completely. Before and after the Fermilab, we learned a lot from Fermilab. And having a Fermilab 10 times better will change our view a lot. Well, CTA is not Fermilab. That's a different thing.
All right, so I'm gonna get a little more. I'm gonna get a little more out there.
You're going to ask the whole audience, right?
No, not necessarily, but sure. Let's do it. I mean, this one goes to Raul, but I also like to hear you guys' opinion, which is, what do you think about the many words interpretation of quantum mechanics?
I don't know. I have a really good friend who'd love to answer this, like Nelson Pinto Neto. He is a specialist on this. I'm not really, you know. Oh, it's wonderful. I would love to.
I'm not going to answer, but you know who living nearby here? David Bohm.
Yes, actually.
Yeah, David Bohm was 100 meters from here.
David Bohm was here in Brazil for a while, actually. Yeah, so, yeah.
I showed yesterday the house. I can show the house there. It's very nearby. It's not his house anymore, but.
You want to ask a question? Yeah. Do you want the...
It's up to you to decide. I don't know. Okay, so my question is going to be a little general. Okay, what do you think, like all of you, would be the most prospective field of astrophysics in the next 20 years? Like most numbers of Nobel Prizes, I don't know, most numbers of finance, something like this. So what should we do?
I have a standard advice. I'm not sure I name a topic, but I have a standard advice to my students. You should look at what instruments are going to be first delivering data at the year you're coming up for tenure. And you should work on those topics the year after you get for tenure. Because usually these instruments are very expensive, takes a long time, and they drive a lot of science. As it gets closer, it becomes more and more interesting, more and more money is going into postdocs, more faculty jobs, and you don't want to be disproven the year you're up for tenure. So it should fly after you're up for tenure. I think so that's 10 or 15 years from now. So. That's why I think
10, 15 years? These people need jobs before that. What are you talking about?
Well, no, tenure.
10 years. Oh, so tenure, yeah, tenure.
But they're your students, so 3-year postdoc, 6 years as
6
a faculty.
years, yeah, 6.
So you should look at things that are going to be delivering data in 10 years.
10 years, yeah.
It's not a question, but to say, one student asked one question, very interesting question in some school in Brazil, in Sueca school. They ask housing and I forgot the name. What's the more interesting? No, what the more hot topic when they finish the PhD? What's the hottest topic when they finish the PhD? And both they say the same thing: the sigma 8 problem. You probably you don't know what the sigma 8 problem is, and maybe I am going to ask you, when you finish your PhD, what is the hottest topic that everybody says?
Mainstream topic.
You want to compliment?
One week after I defended my thesis, so I think it still counts when I was finishing my PhD, Oprah published the result of superluminal neutrinos. So I think that was really the hot topic for, I don't know how many months, 10 months more or less. So you guys are very young. So at a certain point, an experiment called Oprah said that they were measuring neutrinos moving faster than light. It was very famous in I don't remember when I defended my thesis. It's not the Kashas, I think. No, 2011, 2011, 2011. And of course, you can imagine the community was, I would say, enthusiastic slash puzzled slash people believed that there was absolutely no chance that this was true, and of course it was not true. There were really giants of theoretical physics like Glashow publishing papers saying, you idiots, it's absolutely impossible for this to happen because otherwise everything else falls down. And it lasted 10 months. So yeah, it was, but then after 1 year, the Higgs was discovered, so I was happy.
Yeah, the year I got my PhD, the year after was the year when the supernova results came and dark energy exploded. That was about it, but no, I mean, not a lot of people saw it coming.
Yeah.
I mean, some people were, you know, kind of having hints about this, but you know, really it wasn't. Really, it was kind of a bit of a surprise. Maybe Zoltan is. Was it a surprise to you?
So Adam Reese's office. I was a graduate student, and Adam Reese's office was 2 doors from mine, and so it was not a surprise for me. But we were sworn to secrecy. Yeah. The other big thing happened. I think our PhDs were 1 year apart or something. Mine was 98.
Mine was 97, pretty much. Yeah.
The other big thing was the first exoplanets were discovered.
About the same time.
So it was just starting the exoplanet.
A few years earlier it was Planck. Kobe, which was a really big deal at the time. But you know, I think I mean, if you think about, you know, having something new that nobody had before on a massive scale, then, you know, one of them is LSST for sure. It's going to be seeing the universe in a way that nobody saw before. So it's kind of qualitatively a different picture. So that's one thing too. I think the thing about gravity waves is that we had the first few detections, but I think we are, I mean, it's just the beginning. I think if you look at the other instruments, they're planning for the next 10, 15 years. So that's another thing that I think it's going to, I don't think LIGO is seeing the final story. So I think there's much more to come from these. Now that you know that there's a signal, there's lots to be seen, the other ones, they will take it further. So it's like the difference between Kobe and Planck. It's going to be that kind of improvement.
Also, Lisa is a good time scale, 10 years from now.
Yeah, Lisa.
Completely different questions will be asked about the massive black holes. So good topic for students.
Actually, I just want to drink. My question is more personal, but I would like that all of you will answer. When did you know that you want to be a professor and stay in the academy? It was like when you start to study, or just stay? When did you know that you want to be a professor and like continue in the university and research?
Can I answer?
That's a funny way of putting it. I would say never, still today, but you know. But I mean, perhaps being kind of doing this, which is like a colleague of us used to say, you know, we don't work. We never do, actually. We do a 3 hours a week, right, when we teach and so on. But you know, I think it was 13 or something. I read Isaac Asimov. He had a book about the collapse of the universe when black holes form, and that was it. For me, that right there. But being a professor, I didn't even know this existed. I mean,
You know Maxwell David, right? So becoming a professor is exactly the same thing. You need to have something that somehow pushes you in the right direction in the right moment. It's highly stochastic. I think we all agree, right? It's highly stochastic. Yeah. There are many things that must happen. Mm-hmm. And there are many colleagues of mine that were very good, that are not in academia today. I cannot judge if they are happier or less happy than I am. They probably have more money. That's, I'm pretty sure. But, I mean, at the end, what you do is you go and you see what happens. I think that's the best thing I can tell to all you guys. Just go. Just go and see what happens. Some of you, statistically, some of you will become professor. So, now, that's the stochastic part, unfortunately.
For me, I think I knew already from when I was 15, more or less.
Wow.
And the only reason was that I knew that I hate repeating the things. And for me, the research, the only difference is that you are not doing the same thing the day before, the day after. Every day is a new thing, is a new challenge. And that's for me is the only thing that keeps me in academia. Otherwise, I hate to repeat the same job every day. Well, teaching also is 3 hours per week. It's fine. So you have to do something at the end.
You need to pay the bills.
So I think that this latter comment correlates a lot with what Nico was saying, right? There is a stochasticity, right? Because you need to have exciting things be happening around you in your field to have this oh, that's something cute just happened, some new measurement, and you get excited and you push and you push. And I think that, you shouldn't trick yourself. There is no way you have control of your life, right? This is just an illusion in any chance. You can only control your local circumstances.
Yeah, so thanks. That's an interesting question. I think for me, I knew from very, very early age that I wanted to be an architect. Which actually, I'm not joking. In college, I went to MIT, for undergraduate, and I was an architecture major. Until in my second year, 2 things happened. Stephen Hawking published his book, Brief History of Time. And I was really amazed by what was in the book. I don't know if you guys read it. Yeah. I was at the perfect place at MIT as a second-year student. Alan Guth, who discovered inflation, one of the 2 people who got credit for discovering inflation, was a professor there. So I thought I should check out physics classes. And then there was a couple of really nice teachers. So I don't think I ever made the decision to become a professor, but I did get captivated by this stuff. So I did decide to apply to graduate school. I couldn't believe you actually paid. In the US at least, you get actually decent salary as a graduate student. Then at some point I realized professors don't have to get up in the morning if they don't want to. And they don't have a boss generally to tell them what to do, so I found that very attractive.
Okay, I think you won't think that moving me to be a professor is that the example of my previous professors, what they do, the passion they have for the physics, and the brightness in the eye when they see something new, and this thing what pushed me to be a professor. But as everybody said, it's not a linear process. For example, I'm from the south of Brazil, and I entered in Campinas, here in the state of São Paulo, and it was a complete random, because in the year that I finished my undergraduate, the only person that was in practical physics leave the university to go to make a sabbatical. Then I have no practical physics there. I know they want to do practical physics. Then I need to move to São Paulo. And after that, was 10 years with no position open in Brazil in practical physics. And then I need to move for many places. And the end, I finished I went to Campinas. If by luck, we have one position open in the year that I was postdoc there. And I apply. All the other postdocs, they don't apply. I don't know why. I only the only postdoc apply, and I get the position. And okay, I deserved to get it. I entered the position, but it was a series of not choice. No, I moved to something external to me. But I think the more thing is the example of my previous professor. This is what moved me to be a professor. Okay.
Stella.
I'm sorry, it's a very stupid question because I had never have a so deep contact with neutrinos before. So my first question is, because we talk about flavors of neutrinos and not type of neutrinos, is the first one. And the second one is, I think was the first question they asked about you prefer Dirac or Majorana. I have no idea about both of them. Can you explain a little bit more? And the last one, can you give some tips for who is finishing the PhD and need to have your first postdoc? Okay, that's it. Thank you. Cheers.
So to whom is the question? Anybody? You want somebody to start?
Please, look to the picture.
Okay, me holding the bottle, perfect. Okay, let's see here. Arman, you start.
Okay, I'll start with which one was 3 questions? Yeah? Majorana versus Dirac. So the Dirac particles, she's looking at the photo.
That was the point.
The first one was who came up with the terminology flavor.
Yes.
I actually think that's just,
Murray Gell-Mann, no?
Yeah, the Murray Gell-Mann was the first one. Is basically just using a fun word as a type. You can say type E, type muon, type tau, neutrino is fine, but it's boring. So you use color, you use flavor to make it a bit more bearable. You want to go to the second?
No, I have to say what is Majorana and what is Dirac. Tough one for you.
3 questions. I did one, you do.
I'm gonna go there. No, okay. Do you guys know what chirality is? Who knows? Who doesn't know what chirality is? Okay.
Yeah, a few people don't know.
Okay, so you know that there is a Lorentz group because we can apply Lorentz transformation to transform between equivalent reference frames. So left-handed, so chirality is a difference which only arises in fermions. Fermions are strange beasts, okay? Not the strangest that we know, but they are strange beasts nevertheless. So they come in 2 types. One transforms when you apply a Lorentz transformation in one way, and the other transforms in another way. We call one of these types left-handed and the other type right-handed, okay? Now, all the particles in the standard model, all the fermions in the standard model, with the exception of neutrinos, we know they're Dirac particles. What are Dirac particles? They are particles for which both a left-handed and a right-handed component exist, okay? When you have when you have both types, you can construct a term in your theory which is called a Dirac mass term, okay? For neutrinos, it may be different because they can be Majorana particles. So what are Majorana particles? They are particles which are neutral, okay? So they are their own they are their own antiparticle. And for this reason, the right-handed component can actually be a modified version of the left-handed component. So in a sense, you have less degrees of freedom to describe a Majorana particle, okay? I know it's a bit technical. I don't know if you guys have a simplest way to answer the question.
I think the degrees of freedom is the best way to say. For the Majorana particle, you have 2 degrees of freedom, is the difference. So if you remember in quantum field theory, when you describe a particle, you write the particle in two spinors. Is the up and down, when you write the field. Yeah? Is the right-handed and left-handed, and they are independent of each other. So basically, you have 4 degrees of freedom. After that, you apply the equation of motion, you can remove the degrees of freedom. But before is 4 degrees of freedom. For the Majorana, these are not independent. They are depending on each other. You can write as you said, the left-handed can be written in terms of the right-handed. And that basically it means they are not independent and there are just 2 degrees of freedom.
There was another question.
Yeah, advices for people who are finishing their PhDs and want to get a postdoc. Is that it?
Yeah.
Yeah. How to get a
First postdoc.
I can begin. I think the one thing that I said to my students, you need to show yourself. The people need to know you. Then you need to not be ashamed. Many times, I know, you see, I tell my students, I tell secret, I was a student before. Now I know that it's a very frightening to talk in public, to ask a question about a completely different person. But when you finish the PhD and begin the postdoc, it's the time you should ask questions, you should give talks, you should communicate with the people, with more people that you want, because this is the time that people show where you are. Because one thing is it's your name in the paper, another thing the person know how you behave, how you answer the questions. This is very good. You need to show yourself. It doesn't matter if it's a poster or if it's an oral presentation, you need to show yourself. If you show yourself, the people are thinking much better about you, to qualify you, to see opportunities, to give opportunities for you. I think this is what you should do. You should talk to people, and then you can, for example, look and talk with us or the professors. What you have, what you see. Don't need it now. Can be 6 months. Maybe you have another opportunity, some position, okay? And then, okay, next time, did you have some position there, talk, and give, and if it's possible, to give talks, the maximum you can, even in the university. Because sometimes you have a visitor there, or sometimes you have a professor from another thing. He can see you, what you are doing, what this thing. This is the interesting part. Okay. I want to say in my personal experience, my first time there give a talk was in the Brazil National Conference. And I was very happy that I was the rest of the day and said, no, everybody will be tired. Nobody wants to see me. I mean, I'm a PhD student, not interested in my work, they say. But then, before me, you have a very big boss. You're going to give a talk, a small talk, but a talk. Then everybody wants to see what you want to say, and then everybody stay there to see my talk. I was very nervous, saying, okay, my professor there, my professor is there, oh, the professor that I don't like is there, the professor I like is there, everything, all the combination. I was very nervous, but I give a talk here, I think this is what you should do. You need to show yourself.
I find it a little hard to answer because there's so many different types of postdocs which you can apply for, but I think in general, one advice I give to students, you should have a topic in which by the end of your PhD, you know more than your advisor. Which is not a joke, again, it's not a joke. It means that you really become an expert on some topic by the end of your PhD, and people should know about this. So I agree with Orlando that you should give talks. And then later on, you can do multiple topics or work on things, but it's very important, I think, particularly for postdoc stage, to have a few papers where you're showing yourself to be an expert. I think that works for fellowships, where people just look for overall best person. It also works if you want to join a group that works on some topic, and they know you know a lot about it.
Yeah, I mean, that thing of like you are the expert on the field and you can have like capacity to show that you clearly understand the topic is really important. I think what Orlando said about having exposure is becoming easier. We follow these like Zoom conferences and online conferences. It used to be much more difficult to travel. I know it's not ideal. And I know that traveling to places and actually seeing people like on coffee breaks makes a huge difference when you talk to people. So that's what's important. I think that there is something that when I was a graduate student, I was in a workshop and I was talking to Howard Georgia at the time, who was giving a talk. And I asked him, so how did you become successful? He's one of the founding fathers of the standard model. And he asked me, well, that's the wrong question. Where he told me, that's the wrong question. I think the important thing is to figure out what's the skill you're actually good at and try to understand how that skill can be used in an impactful fashion. There is a tendency that when you see successful people in academia or in different topics, you see like, that person is very successful, what are they doing? And then you try to mimic what they do, but this person's skills are totally different than yours, and then you end up in a catastrophic situation. And so just be sure that you have to be an expert, but don't try to imitate somebody else, just figure out what you're good at.
AJ, do you want to do the full deal? You want to do the full thing?
I never had, but I would like to have today. So I have a couple of questions. So my first question is, how much we know about the universe today? So like in percentage.
5%.
Really? You know about the 5%?
General refill, otherwise. Who wants to start? Oh. There you go.
I mean, I was mentioning 5% because of the, baryonic matter and dark matter and whatnot, right? I think, I know, I'm a particle physicist by formation, and it sounds like we're always learning things. Like in the last 5 years, this whole new domain of gravitational wave astronomy sounds like it's opening frontiers. So, I don't know. I will relay the questions.
I don't know. Because we don't know how big is the thing we don't know. I can't code a fraction, but 5% is a good one. I'm always impressed by how many options there are to work on very open, very big problems in astrophysics. I think it's actually particularly attractive about our field. There are numerous open problems.
And and how and how multi-messenger astronomy will help us to explore the universe in great manner? How multi-messenger astronomy will help us to explore the universe in great manner in upcoming few decades?
Oh.
I know, I think it was interesting from what Armand was. Clearly, we're making progress here. What Armand was saying in his talk, right, and I was trying to echo the same in one of my lectures, we have seen the universe in light for thousands of years, and we have identified sources and categorized the universe in that way. But now we have these, neutrino sources, and they appear to be dark. So maybe if you were to have seen the universe in neutrinos from the beginning, you have seen a different particular way of organizing it. And I think that could be interesting.
Yeah, so I just want to know, is there any mechanism which present outside our Earth who accelerate the particles to the great energy, 10 to the power 21, 22, 23, but still based on our instrumentation we can detect up to the GZK cutoff. So in upcoming years we'll be able to detect those kind of energy about 10 to the power 21, 22 G.
I mean, in some sense, the cosmic ray experiments are detecting those cosmic rays, or those energies, but we still don't quite know where they're coming from. But I do feel that we're making a good, about 10 years ago, like what Armand was saying, that we thought the gamma rays and neutrinos were much more correlated. It's now clear that these objects are not quite as correlated. So we are learning about it. We now know that these neutrinos are produced order tens of Schwarzschild radius from the black hole of the AGN. And so I think that we're learning from those, and maybe in the next 10 years we'll figure out those acceleration mechanisms.
Yeah, okay. You want to say something?
Yeah, I think we will be able to probe the energies higher than 10 to 20, 10 to 1. We have to find the ways. One of them is the one that I was saying. You look at the neutrinos that are leaking from these sources in the very high energy. Of course, you cannot look at, you can receive cosmic rays with the energy more than 10 to, above the GZK 10 to 19.5 if the source is close. So if it is less than 40 megaparsec, then the GZK is not effective anymore. Yeah? So we can receive the cosmic rays that are for the local sources, let's say local universe source, and with the energy more than 10 to 21, 2, if there exists. But if you want to go to the other messenger and also cosmic ray in the higher energy, of course you have to go to a neutrino. That's probably the only way to probe. Gamma rays, no way. Cosmic rays for the distance more than 40 megaparsec, no way. And then gravitational waves and neutrinos.
Okay, thank you.
Can I add something? I think there are two things which I think are most. I think neutrinos and gravity waves are the ultimate way to go because everything else is transparent to them. You generate them, that's it. You're not going to kill them off, and you can see the whole sky. We'll never be able to see the whole sky no matter what we do, right? But with gravity waves, we can see it all. We don't care the whole galaxy is in front of us, we can still see. Neutrinos, I think it's probably the same thing, right? I mean, there are some details to be worked out. For gravity waves, there's nothing. You just have something behind 1 cubic light year of lead, and you still see the whole thing as if nothing is in there, right? So that I think is pretty cool.
Can you take a picture?
Okay, so we have, sorry, he wants a picture. We can take a picture. All right.
Thank you.
We can all take a picture like that. Do you want the...
Sure.
Sure.
So, Zoltan, I was outvoted on the EM stellar mass lecture. So, there are some papers saying that nearly 50% of LIGO-detected black hole mergers would have been in AGNs and conducive to creating electromagnetic counterparts. So why do you think we haven't seen one?
Yeah, thanks. Actually, I agree with you. I would have also voted for this because in the last 2 years I mostly work on that topic, but I was feeling like I should cater to the audience. I think the simple reason for this, well, we don't know the answer, but could be that they don't actually emit light and none of the LIGO sources are from AGN disks. But there's an obvious other reason, which is the LIGO error bars are so large that black hole mergers, it's very hard to associate with that particular source. So there might have been stuff going on in the sky, we just missed it. I should also say, actually, I don't know if the other people know what we're talking about. The LIGO mergers, there are 2 main channels which have for years been proposed they come from. One is the mergers, so most massive stars which leave behind black holes when they die, actually almost all of them are in binaries, but like 90 or 80% of 30 solar mass stars are actually in binaries, but they're too wide to create a merger, so you have to arrange very intricate evolution of this binary to actually create a LIGO source. That's one. The second one is just black hole remnants of stars in the center of a galaxy or in a globular cluster. They're just billiard balls and they scatter each other, and when you have 3-body encounters, you can form a bound binary. And then recently, my group and a few other groups have proposed this idea that the accretion disk of a nuclear supermassive black hole is a very conducive environment to make mergers because you have dense gas where you can form binaries efficiently. We know massive stars form in these disks, and you're continuously surrounded by a massive dense gas which can drive together the binary to small separations, cause the merger, and you have a chance of producing some kind of counterpart with this dense gas around. So I should lastly say that there is a claim. People look through a data set called the ZTF data set, which I mentioned in my talk for quasar variability. There's a claim that there are 7 flares in the ZTF catalog which coincide both temporally and spatially with 7 LIGO events. If you give me one more, I will tell you that I don't particularly believe those because you have to outshine the whole quasar with the stellar mass black hole. So that's the main challenge, to create a flare that outshines the host quasar. So there's a little difficulties there, but I think it's definitely a growth area for the future. Good thing to get into. There'll be lots of time doing surveys. Lots more LIGO sources.
Thank you.
All right. Yeah, cheers. Thanks for bringing up the topic.
Yeah, no, we have 2 other people here, and then you back there. You already had a question and you drank one. Also a question for you there. Okay, so 1, 2, 3, 4, 5, 6, 7. Oh, gee, I lost count already. Okay. Yeah. You want another one?
Yeah,
Okay.
this one.
Okay, you ask a question, I'll
Okay. So I think mine is more of a personal question as well, because we work really hard to do our masters, our undergrad, our masters, and PhD, then postdoc, and the perspective for a permanent position after that's not really good anywhere in the world. I've talked with many people, and it's like 10, 20, some people nearly 30 years looking for a permanent position, and it's really discouraging. So,
Okay, I can say the same.
Yeah.
It's a perspective.
Yeah.
When I finish my PhD, you have no position for 10 years. No, but now it's much better. It's not 10 years.
It can always be worse.
Yeah.
Thank you.
I think I have a slightly not better,
Yeah,
more
well, I mean,
positive answer to this. I think
Yeah,
is
please.
that I don't think if you actually enjoy doing this stuff, I don't think you're risking much by going to a postdoc.
Yeah,
Because
yeah,
if you're
but
going to
I also enjoy staying somewhere for more than 1 year. That's also,
yeah, but well, so postdocs, I just postdocs, like 3 years usually. I thought most postdocs that I'm aware of. No, I agree. 1 year postdocs sound not so attractive, but if you have a 3 year position, I generally would give the advice you don't have to yet worry about. There's a natural sorting, or people who are most interested tend to stick it out. I think actually you have a much higher chance of getting a faculty than you would just get by simply dividing the number of faculty jobs by the number of PhDs, which is very small. Because a lot of people leave during the postdoc, or it becomes sort of naturally selected who are the most interested, most productive postdocs. And among those, there's a very high success rate, I think, of getting some kind of faculty job. I think it's very dangerous to try to be a faculty at one particular institution. But there are, I know because I write recommendation letters, some years almost 80 or 90 faculty jobs are for which I have written letters, so there are lots of options. And I think the decision point is after postdoc, and then it's more easy than you would think as a PhD student. In fact, the other thing I can say is there are actually very few people I know who are seriously disappointed because they really wanted to get a faculty job and they didn't. I literally know very few.
I know a lot.
But did they leave when they were students or after postdoc?
They're postdocs and finishing PhD students. All of them really worried how they're going to pay their bills.
I know they're, well, I'm trying to make you not so worried. It's just somehow the postdocs who finishing and are not ending up leaving academia, I think they kind of knew for a few years. And at least in astronomy, where in my career of few dozen, they actually end up getting very good jobs outside academia. And they don't seem super depressed at all. And it's not a big surprise that they tried. I do have examples, but they're very few. I mean, less than 5 I know, who actually tried hard for 3 years and couldn't get any kind of faculty job. Is very few. We can talk more after.
Okay.
So I think there are some different realities also in different countries. Brazil is, I think you have that reference in your head, right? So it goes through these. It's like a roller coaster, right? So for many years, yes, there were no jobs. When I also got a job here, we didn't have jobs for many, many years. I remember that when I got a job at USP, I needed to come back to Brazil because of some bureaucracy, crazy. Too long story anyway. But I remember my job there, the process there was like had 45 people for one spot there. So it was really tough. But then it got much better. And then it got much worse. And now it's getting much better, actually. So the problem that we're having for the next couple of years is not a problem of having few jobs, it's having too many jobs. That is going to be the reality in Brazil for the next 3 years, 3, 4 years. Few people and too many jobs. That's the reality here. It fluctuates too much. So we are a relatively small pool of people, and it fluctuates a lot. So, you know, it's a very good time to get a job for the next 2, 3, 4 years here. Excellent time to get a job. So be optimistic. It's going to be easier. Much easier than it was for people that were graduating maybe 2, 3, 4 years before. And then they had to do 1, 2, 3 postdocs. And then also the postdocs we didn't have enough money for postdocs, just a few. So it was a really hard time. So, but right now it's actually looking pretty good. The other thing I would compliment with Zoltan is that my colleagues that did PhD with me, half of them went to academia, half of them did not. I can truly say that the ones that did not are doing pretty darn well. And they're pretty happy also. I mean, come on, physics is fun, but it's not the only fun thing to do in life. And you come out with an education in physics, you can solve pretty much any problem you want, and usually you do. Actually, I think in the US, which is where they have a lot of data, you get this ranking of the highest paid. You graduate in some field. I'm not sure if it was graduate or PhD, and then you ask how much money. It's not happiness, huh? It's money. Well, it's not the same thing, but you know. And then the top one is doctor, medical doctor. Of course, in the US you make a fortune. But then second and third are astronomers and physicists. Not because they're necessarily working in that, it's just because they do a lot of things and they have a lot of choice. So, you know, anyway, I wouldn't be too worried. Not now.
Okay, thank you.
Yeah. Yeah, maybe somebody else can answer this.
I tell you, when I finished my PD, I have 5 years of postdoc, and it was supposed to be 4 years outside, but then I have a position before that, and I think that the people are very open to this. No, I have people get offers from Taiwan, from China, from ICTP, Italy, this thing. There's many places that. But the problem, you need to apply for things. You need to go there to things. For example, SAM. SAM discovered that very few women apply for postdoc positions at SAM. They want to say, if you are a woman and want to apply for postdoc there, it doesn't mean to Europeans, it can be the thing. They are very welcome to apply there. Then they tend to discover there's many options. You say, like in Spain, a lot of things. There's some special type of fellowships of the fellowship from the regional fellowships. There are many options. The point, you need to be looking for this thing, no? And you need to open the eyes. Don't say, no, I want to go to a postdoc to the guy that my professor knows. It will be complicated. No, maybe you need to take a chance to apply for different places, and show yourself. Then it's the best thing for the people to understand, to see your work and what you are doing. No?
Please. long weeks. So I have 2 questions. The first one is a particular one. The second one is more general. The first one, Carlos, you gave us a little sneak peek of some interesting Ice Cube results that are coming out or have come out recently, but you had to skip all the neutrinos and dark matter parts. So I was curious if you could give us a little briefing of what you were going to say about that, and maybe if there's any interesting results you're thinking about commenting on. And for everyone, kind of tying about what Orlando said, it's important to get your work out there and be able to give talks and etc. So I was thinking about if any of you had any suggestions of non-recurrent events, be it workshops, schools, or conference that you thought were very interesting to get to know more about your area, or maybe devote your work out there that you would recommend for anyone here to attend.
So let me say something on the second point you mentioned, which is maybe easier. There is a conference called TEPA, which is TV Particle Astrophysics, which I think this year is in Italy, in Naples? Napoli? And I think that's a very good one. If you do astroparticle physics, high energy at least, it's really popular, and I like it because it's, I would call it medium format size, so you can actually talk to people. So that's a good one, and it's every year. There is also the International Cosmic Ray Conference, which is every 2 years, which is nice. If you're into neutrinos, there is a neutrino conference also every 2 years, so once next year. But that one is more like low energy neutrino physics, so maybe not so relevant for this group. The dark matter things that I skipped, the fact that neutrinos are neutral, allows for 3-level couplings with dark matter in principle, which is unique. And I think that opens up the possibility to look for both direct annihilation for dark matter to neutrinos and also the possibility to look for neutrino scattering. And so this is interesting, I think, for 2 reasons. First is, the WIMP miracle requires dark matter to, annihilate to certain more particles. It actually tells you which particle it has to go to. It just has to go at a given rate. And so we have constraints for that from like gamma rays and other messengers, like cosmic messengers. And that sort of rules out a big chunk of the WIMP parameter space. But if you actually look at it for the most minimal scenario of WIMP, if like dark matter just goes into neutrino, this is actually not ruled out. You can write a very simple model. This just works fine. And what's interesting, I was going to mention in my slides, is that another S-cube but KM3net is going to actually reach that WIMP miracle scale when they operate in next years. And the reason is that they are actually looking, because they're in the northern hemisphere, they can look through the Earth and they look at the galactic center very efficiently. So I think that's exciting. And then the other thing is, there is a category of neutrino mass models, which are known as scotogenic mass models, which is when neutrinos acquire masses through dark matter interactions. And those also motivate some kind of neutrino-induced opacity in the universe because of ambient dark matter. And so that's relevant for light dark matter species. And I think that's something that we're also having a look, and I think it's also interesting.
Aren't scotogenic models already very well constrained, or am I thinking wrong?
No, it depends on the parameters. I'm not sure which one you're thinking about, but I think it's okay. I'm going to play. There was a question of conferences.
Yeah, okay, yeah. For example, now the Invisibles school, this is a very good way. And I have a history that some person get a postdoc because she traveled 10,000 kilometers from Unicamp to get a position in USP. They go 100 kilometers apart. But the person didn't know. But this is because the person went there to give a talk, and then the other people know that what she was doing, and then they hire the person. This I think to go to this school, there's the astroparticle school now going to happen in CERN. You should go to this place, Of course, you have this lucky, there's so many schools there. I think you should learn it. Sometimes you can't get the full funding, but most of the funding you get, and then you get from another source, and go to these places, And it's a good way that you show yourself, And if you have some events, for example, national meeting, to talk with the professors that are there, also. And then you can get options for what we're going to do, okay?
Is it all? Okay.
Can we get more?
Yeah, sure. Samuel.
Due to the fact that dark matter and dark energy are related with astrophysical large-scale observations and somehow related with gravity, could it be that in order to have a better understanding or a good explanation of what they are, we need to go beyond our current paradigm of physics, and we may need a better understanding about what space-time and gravity is? It's for everyone, I guess. But
I didn't hear the question. I was serving people. Some of you are.
Well, yes, in principle it can be, but you need to find another framework which is as successful as the one we have now, and at the same time gives another interpretation of dark energy and dark matter, which I think is not completely trivial. But if you give sufficient time and sufficient paper to theorists, I'm pretty sure they will come up with something. No, I don't work on this exactly, so I'm not sure. I guess there are theories of modified gravity that try to do to add ingredients, but my impression is that if you want to just stick to minimality, And so you have a spin-2 massless particle that mediates gravity, and that's it. There are no many other options around. But that's my impression. I may be wrong.
So, well, my second question was if gravitons exist and why, so I guess...
Well, I mean, you can quantize general relativity. Okay, it's not a theory which is valid all the way up to the mass scale, to the Planck mass, but there is absolutely no problem in quantizing general relativity at low energy. Now, if you're asking, will we ever be able to detect a graviton, a single graviton, as we are able to detect a single photon? My bet would be no, because the interaction is so tiny that I don't think we will be able to actually detect a single graviton. But I would be, on the other hand, very surprised if gravitons do not exist. But again, that's my personal take.
Yeah, I should add that the most popular theory for the origin of the fluctuations in the universe is inflation, and it's perhaps a misunderstanding to say that inflation generates these fluctuations by quantum fluctuations of the scalar field, so-called inflaton. It's not correct. It's actually, if you do perturbation theory of a scalar field with gravity, what you're quantizing is a mixed degree of freedom between gravity and the scalar field. So in some sense, you are there already quantizing this, and we rely on this for things that we observe. So in some sense, it's already there, except that it's kind of a constrained degree of freedom. It's not really the graviton, really. Graviton is yet another degree of freedom. But in some sense, we are already doing that. So, it's, I think there are some holes in there, but, we are already doing this, and nobody's pulling their hair saying, no, everything about inflation is completely off because we are quantizing gravitational, degrees of freedom. No, we already do this, so.
Okay.
Yeah, if I may add something, I mean, you have when you get your first course on quantum field theory, you get the idea that a field is something which is sculpted in rock, but it's not. You can redefine fields, as Raoul is saying. You can mix fields. There is absolutely no problem in quantizing mixed fields. Fields are, as I was mentioning yesterday, they're just useful tools that you use to describe many-body quantum mechanics and put their special relativity. That's it. Then you do whatever you want, as long as you are coherent and you don't mess up with the math. Don't mess up with the math. That's important.
So who is next? There's a line here, so I guess it's you. Then,
okay, so my question is, it's about science, but about the structure in which science happens. That's the academia. If you could change something on how academia works on your context, what would it be and why?
Somebody want to? Okay, I give my take. I'm speaking about particle physics now. Okay, I don't know the other fields, so probably it's going to be diametrically opposite. I think many times there is too much aggressivity, which I think is kind of ruin, because it seems that it's a race to who gets there first and not who has the best idea. And I think especially for young people, this is pretty bad, because it forces you to become aggressive, and there are people that really cannot become aggressive, which I think it's a con, it's not a pro. And these people have huge difficulties in presenting talks and so on. So this is definitely something that I would change in particle physics. And another thing, I think there are people that really become fanatics, as we were mentioning earlier. I think we should be more open. I mean, nature always surprised us, and already the standard model is, although it was the simplest possible thing that Weinberg could do, but then when we started to discover the second generation, the big question was, what the hell is going on? Why is there another generation? And then the third one came. So why the hell is there a third generation? I mean, of course, a posteriori we know, okay, without third generation, we couldn't have CP violation. But a priori, we could ask, why the hell should we want CP violation, right? So you see, nature has always a good and healthy way of surprises. And there are some people that really believe that the theory they are working in is the ultimate theory and that is that. I think many people in particle physics should be more open-minded. It becomes kind of religious zealots when we should be kind of the opposite. Oh, I think it's a mixture of cultures, yes, as Armand is saying. I think you have a global community, or almost global community, where different ways of approaching things, mixture, and in this process, I think the people that actually shouts more and is more assertive is able to communicate more easily its result.
There's a bit of an arms race that goes on,
yeah,
right? And
exactly.
It's a reduction
There's a bit of an arms
to
race.
the minimal,
yeah,
to the maximal aggressivity in some sense.
Exactly, and there is if I may say just the last thing, I think there is also a very wrong attitude with papers that turn out to be wrong, which are now people, if people publish papers which turn out to be wrong, maybe because they missed something or because there is some small detail that they got wrong, people get ashamed for that. But actually, I think that's where you learn things, right? There are famous cases in the community that, of course, I'm not going to mention now. We can talk later. But there are famous people that are still nowadays, people say, but he got that wrong. Okay, who cares? What's the problem? Then he got 10 more papers right. So, okay. We are here just to, it should be a collective effort to progress, right? And not always, I feel it's not always the case.
Like Einstein, for instance, right?
So, I'm going to also give like a particle physics sort of opinion because I'm more on that front. I think there are three things that I will actually do change that I think are bad for especially young people. One of those, the first thing I would change is that I will move from a alphabetical ordering system to an ordering system that actually weights contributions of authors in our papers. I think that's very bad. I know that the astronomy community has actually a longer tradition of doing this, I think, correctly. In the particle physics, for whatever reason, even though sometimes we have 2 authors or 3 authors, we still do alphabetical for no real reason. I think this is bad, and it actually correlates with what Orlando was saying earlier. Young people need more exposure, and it's good that their names are out there. Big journals like Nature or Science do actually ask you for author contributions, and so if you publish in those, you will get who did what. But in other journals, that's not the case, so that would change that. Another thing that maybe is more controversial, I will argue for a double-blinded reviewing system. That actually, double-blind review system means that you submit a journal to an article to a journal, the referee doesn't know who you are and you don't know who the referee is. This especially hurts people who submit journals or papers from not well-known institutions or countries. And so I think that really hurts diversity in our field. And then the other thing that, but this one is actually kind of changing. We should move to our open science, open data science, but that's actually happening already. Experiments are putting their data out, people are doing that. That's also, in some sense, astronomers have it much better. They're actually doing it for many years. But in particle physics, we're going that direction.
Yeah, about this thing, about the thing of alphabetical in particle physics, this is hurting a lot of the new students because everybody else is judging particle physics for the standards of the older class, and the students being hurting. For example, this school is not good because it's the first author, or is it the middle author? I don't know who is in the thing. And then the students are getting, they're not evaluated equally as the older students. And because this, sometimes you change the rules, not of alphabetical, because the students are suffering this thing, no? And another thing for this double bind is also because of the gender. The gender is not physics, but the gender changing the behavior of the people. What you think is, no, if some girl going to give a talk, or one guy going to give a talk, the people change. The attitude, I'll tell you some example, some person, I will not say the name, the person, in the first seminar that she gave in Brazil, when she gave me, she was, for 1 hour, she was attacking for a lot of questions, They say, why do this? The person tried to prove if he was, if it the correct person to be there. And I never saw this. I only saw this in seminars given by women. Here in Brazil, but also in the United States. And they are very aggressive, very aggressive. And then the women that survive, the women that they are, you say, I don't know to say in English, that something they enter in this eye here and they get out of here. The person doesn't become bothered because of what the people say or the aggressivity of this thing. And then this is something I think you need to change, you know. And you know, the physicists also are people, no? Because they are bringing what they are doing out their lives, this thing, but you need to have these changes, no? To behave more equally and not judge the people by the cover, you know, what they think, but what the person is made a contribution, this is one point, no? And if you can have this double binding, it can be a very good thing because there are some very nice articles that not get published, and the other articles, you look at the articles and say, they're no news. Okay, the guy is a big boss. One thing that happened once for me, one person was doing some work, and then the work was not good. This is the point, no? But they say, if I include in the name of my supervisor, the work will be approved. They say, no, doesn't matter if you sign it or you the supervisor sign the paper. Doesn't matter. It's the content, no? But sometimes the people think about how you put the name of big boss or this thing, you can get in my paper approved, no? This should change, no? They say, it's not everybody, but sometimes it happens. And this, you became me, oh, why this happen, no? But many people worry about this, about the thing of gender, of the where you are, where your institution is, because some people publish very good articles for very small institutions, and they're very good quality. But okay, it's not the teaching in research. What you do, no?
Douglas. So my question is more about your personal experience in academia. So do you have any non-academic advices for surviving the academic life? I mean, I don't know, work-life balance, go out in the weekends, drink some cachaça. I mean, something that was important to you during your PhDs or postdoc, etc.
Have friends.
Have friends. I want some. How? I really want some. Let's go. I just want the shot. Okay, go. Go. I mean, if you want to say something, thank you very much.
I think, what's your name, sorry?
Gabriel.
I think something you need to do is to separate what the work life and your personal life. No? Sometimes the people get mixed these two things, no? And say, okay, you're probably going to have very good friends here, this thing, but also have your things to do, no? I don't know, to do RPG, or to see movies, or to see the sunset, to do some hiking, same thing, no? The same. No, I see RPG because I have some friend of mine, they say they are going to do RBC this weekend, then they cannot meet me, or this thing. And you should something to do, no, something to like, you know, something to do. You want to see, okay, I want to read a book, I know, or you wanted to go hiking, this thing. There are many people that I know that I think that they are very good that, okay, they have the scientific life, but also have this personal life to do things. And as I say, the weekend is not from the supervisor. The weekend is for you. You should, they say, you don't need to answer any email in the weekend. They say, you don't, this. And no, but sometimes you say, me myself, I send some emails in the weekend, the thing, but I should not, no, to say, because the person is to do other things, no, and but I think something that I think to have is the respect. The people should respect you. to see what you are the person. You are not a copy. Sometimes the people think you should do a copy of me. No, it's not this. You do your things different. No, I have students in the PD that they are electrical engineers. The philosophy of the life of my student is completely different from mine, but I have very good relationship. A completely different person. The person did the PhD in physics, was very nice. He had a completely different experience, but it's a different thing. It doesn't be a copy of myself. Sometimes I think the people think that you should repeat copies of yourself. No, the person to be better than me, in different ways. So something I don't know do. No, I did a joke here. For programming, I stopped in 77. I made my codes in Fortran 77. No, but the others said, no, you should go in Python, Mathematica. They said, okay, no, I stopped in 77. No, everything has something to add, some new thing to add, you know. And I think this you should do. You should separate your personal and work life first. No, it doesn't matter if your supervisor you like the supervisor or not. It's in terms of that. It's not this. Separate. No, sometimes education meets the things, because when you finish your career here, you go to another way, you're going to move. No, you're going to do in this new career. You supervise, no. You have to do your things. Okay.
Okay. So I just want to be a bit more realistic, because it's nice to say that separate your life, enjoy your life, weekend is for you. But to be honest, I think all of us can confess, we passed this phase. You have to work a lot. You have to work hard. Weekends, New Year night, Christmas night, any day. You have to check your email. You have to answer the emails. You have to do the calculation. You have to write the code. It's not like this that, okay, I do the science, I enjoy my life 5 days per week, and then 2 weeks I go just forget about anything. And then, no, it's not this. We passed all of this. You have to work, of course, separate your life, but be prepared to fight for what you want. If you want to be the best, you have to work a lot. And it's not this that, no, it's easy. No, it's not easy, but I believe if you are prepared to pass this phase, is much better than suddenly go there and sit, and now you don't have time to do anything. Be prepared that you have to work hard.
I was going to say something very similar, but I think that the first thing is to recognize that this is not an easy thing. Like, doing something new is never easy, and you're doing something that's new, and you have to do it better than anybody on the planet, so that's clearly not a trivial thing. And so, but I do think that there is something important in having a support system, right? And having friends and having and it cannot be that your support system is a single person, because that's a single failure point issue, which is not a good idea. You know, it's diversify. You know, it's also good to have good communication with your advisors or other mentors. It doesn't need to be only your advisor. It could be some other faculty in your departments. It could be like somebody that's in charge of student mentoring. I think you will find that there are people really willing to help. And so having a good support system, I think it's, recognize that this is not easy, but plan for it.
Yeah, I think the only thing I would add is I think actually we have a privilege in the sense that, so I often hear an argument that, sorry, this might be a controversial statement, but I often hear an argument that why do we take our work home, and after 5 o'clock or on the weekends we still have to work. But it never resonated with me, because I think actually it's a privilege that if you're really interested in what you're doing, there's no natural cutoff at 5 o'clock. So I've never thought of this as a separation between work and life. In fact, the vast majority of people I know in the field have their friends and sometimes their spouses from the field. So maybe that's not particularly healthy, or it's a bubble, but I think it's a privilege to be in a bubble. So I actually don't see it as a criterion to separate the work and the life. On the other hand, I do agree with Carlos that you can't just be working all the time without some support system. So it's important to have those hikes with your friends, when half the time you might discuss the black holes or the neutrinos, but half the time you admire the trees. But I don't see a natural need to segregate work and life.
So I think this is the perfect time to stop and impose a break now on the work and life in some sense.